Hello, everybody. I'm happy to present you with Stephanie Weirich. She is a professor in the University of Pennsylvania, and she's a professor of computer science, and she's going to be giving the next talk. So I'll let you do it.
Okay, thank you, Alberto, and thanks to the Haskell Lab organizers for putting together this conference. I'm really excited about it. So today I'm going to talk about implementing the lambda calculus quickly. And before I begin, I want to point out that a lot of the material and the code that I'm going to discuss with this talk, and even the slides themselves, are all available on this GitHub repository. So if you want to check it out after the talk, you can definitely see there's everything I talk about today and much, much more there. Okay, so let me talk a little bit about the lambda calculus, and I'm not going to talk about everything about the lambda calculus, but I really want to narrow down to a very key operation that when you're implementing the lambda calculus, this is something that you have to think about. What does it mean to do capture avoiding substitution? And a mathematician might write capture avoiding substitution like this, where we have some lambda calculus term A, and inside of A, there's a free variable X, and we want to replace that variable with B. Sounds very straightforward, but there's this one thing about substituting into lambda terms, and that's we have to avoid capture. So if you look at this particular example, you see that here the variable z appears freely twice in this lambda term, and we want to replace z by the variable y. But in the second occurrence of z, that's underneath a binder for y, and we don't want to naively go through the term and replace that. And we don't want to naively go through the term. We have to rename that binder so it doesn't capture the new free variable y that we put in. Right, and this is well known, and there are many, many ways to implement it, but it is also notoriously tricky to implement, right? And so even as I was preparing for this talk, I saw a tweet earlier this week that really resonated to me. There's a lot of people out there who spend a lot of time implementing substitution functions, right? And so when I say let's implement the lambda calculus quickly, one way of interpreting that is kind of like this, right? So let's kind of declaratively create our data type for the lambda calculus, where we have constructors for variables, we have lambdas, and maybe we're going to mark that that lambda is a binding occurrence for variables, and we have applications. And wouldn't it be really great if we could just say, okay, now derive a substitution function for this lambda calculus expression. And just one little line of code would give us this definition of capture avoiding substitution. It would be correct no matter what lambda calculus expression we had, and we would not, and no one would have to spend any time debugging our implementation. Now this sounds great, but it actually turns out that this is possible today, right? So there's several binding libraries out there that are available for doing exactly this. So this is an example of, I've decorated the term with some constructs from a binding library called unbound-generics. And if you import that library into your project, you can use the definition of the bind type from that library. There's a type for variables called names in that library. And that, more importantly, that library uses generic programming. It uses GHC generics, so that all you have to do if you want a definition of substitution for that library, you just create an instance that just explains where the variables are in your data type. That's all the information that the library needs to know to correctly give you a substitution function. Right, and so really, this is the quickest definition I know of substitution. But perhaps you thought I meant something else when I said, let's implement the lambda calculus quickly, right? And it turns out that there's lots of implementations of binding libraries out there on Hackage, right? But maybe we do care about how fast they run, right? We want our implementation to be quick. And this is a really important question, because if you go through and you benchmark these binding libraries, you can see that the difference in the execution speed, so this is one benchmark that I ran on it, can be quite dramatic, right? So it's a really important question to also ask, what's the fastest way to implement substitution for these binding libraries. What does bound do that the unbound generics and these nominal libraries are not doing? Right, so this is a very stark difference here. So why do we have that difference? How can we understand what the source of that difference is, right? And just sitting there, you might think about several reasons why we might have such difference in running time for these different binding libraries. They're all doing the same thing. They're all running the same benchmark. You know, they were created by different people. Maybe some people were better Haskell developers than others. Maybe the libraries themselves support lots of additional features that themselves have some overhead. Maybe one of those libraries found exactly the right GHC pragma to make them go really fast. Maybe, well, all of these libraries use completely different mechanisms for generic programming. Maybe that makes a difference. Maybe they employ internally different optimizations of implementing the lambda-calculus and substitution. And maybe this is the one that you were thinking of. Maybe they just fundamentally are representing lambda terms differently. And so they actually, the substitution operations are different between those different implementations of the library. And this is true, right? If you go and read the documentations of these libraries, the nominal ones are giving a substitution using a name-based encoding. Bound is based on this idea of the Bruijn indices. And unbound-generics is using this mixed representation where it's got names for free variables and indices for bound variables, right? And what I'd like to know is really what does the different choice in binding representation, what difference does that make to the running time of these binding libraries, right? And so just benchmarking the libraries by themselves isn't going to tell me the answer to that question because there's all these other variables. And so I need a way to kind of hold everything else constant, right? So maybe I'm going to start from scratch and kind of re-implement these three different approaches. Maybe I'm going to make sure that we're only focused on the core mechanism so that we don't have any other confounding features. Maybe I'm going to, find that magic GHC pragma to make it all work. I'm going to look at the impact that generic programming has on these different approaches and benchmark using generic programming and not using generic programming. And I'm going to try to optimize these three fundamentally different approaches to variable binding and see if there's some ideas that can cross-fertilize between these different representations. Right, and so more generally, I'm going to start with three existing, very simple, basic implementations of capture avoiding substitution. One that's just based on names and it avoids capture by renaming bound variables where it needs to. One based on the Bruijn indices, and one based on a locally nameless representation. So that's capturing those three very common classes of implementation. I'm going to look at ways that we can optimize all three of these approaches and see if what difference the optimization plays. And I'm going to make sure that all three of these, when I create these optimized versions, I still want to make sure that I can get a generic binding library out of them. So I'm going to make sure that I can give them this generic interface via type classes and GHC generics, and they're all going to have the same generic mechanism, so that is not going to be a difference between them. And then finally, I'm going to benchmark. I'm going to run some benchmarks on all of, so there's going to be lots of different implementation. I'm going to compare them all to each other. Okay, and my inspiration for this project actually comes from a while ago. So this is a draft paper that is actually, it's a literate program by Lennart. And in this draft paper, he showed 4 different basic implementations of the lambda-calculus, and he showed how to use those 4 different implementations for computing normal forms. And a key part of computing normal forms is substitution. And so we have 4 different implementations of substitutions. So this literate Haskell paper, it includes all the code, that's going to give me the source for 2 of my implementations the locally nameless representation is not part of this work, so I'm going to get the locally nameless representation from somewhere else. But what I will also do is I'm going to get the benchmark from this code. So Lennart included one benchmark at the end to kind of compare these different versions. So I'll start off that as my starting point is using this benchmark. And let me just say very briefly of what this benchmark is. This is the benchmark that I was using to compare all of the binding libraries earlier. And what is it really? It is taking the church encoding of this little Haskell term. 6 factorial, is that equal to the sum of 1 to 37 plus 17? Let's church encode that. And if you church encode it, and if you think about it, really what the church encoding is asking is the number 720 equal to the number 719. Now, through this encoding in the lambda calculus, it's a pretty big lambda calculus term. And computing its normal form, reducing this so that it's the church encoding of false, that takes a lot of steps. In fact, it takes almost 120,000 steps of substitution, right? So as a benchmark, we're going to be calling our substitution function many, many times, and we're going to be calling our substitution on the same term over and over again. So I think this is a really fun benchmark when we are comparing implementations of substitution functions, because it really is exercising this operation. Okay, so now before I go any further, I want to give a little bit of background, right? So I want to make sure that everybody understands these 3 different variable approaches. And so I'm going to work through a normalization example just so that we can see exactly what's going to go on as a substitution happens using each of these different representations of lambda calculus and each of these different implementations of capture avoiding substitutions. Right, so first let's just start with a named approach. And again, this example is to point out certain things that happen that you have to think about when you're computing normal forms, when you're doing substitution. And so here's my lambda calculus term that I'm going to use for an example. We're going to normalize this term. Don't try to think about what it means. It's not it's not like a combinator or anything. It's not an interesting lambda term. I picked it just because it kind of shows off some of the operations that happen when we are doing substitution using these different forms. So we're going to normalize this term. It starts with 2 lambdas, lambda w and lambda x, and then inside of it, there is 1 beta reduction that has to happen to compute the normal form of this term. Right. What we need to do is we need to take this variable, bound variable y, and we're going to substitute for it in the body of this lambda expression. And here's our argument that we're going to substitute in. I made it this triple x so you can really see it. Okay, so what happens when we substitute? You can see I've color-coded things. The y's that we are substituting for are all blue in this example. So we're going to replace this y and this y with the triple x term. We're not going to replace this y because that refers to this binder, not the binder that we are beta reducing. Right, and so here is our example. Notice also we had to avoid capture. So here, this y is underneath a bound variable x, but x appears free in the term we're substituting in. And so we had to rename that to z. So you can see we had some renaming that had to happen while we were computing this normal form. But we also had an opportunity for optimization. We got to a point in the term where there were no more free x's that we were substituting for. Or I mean free y's, and we knew that because we had a binder for y, and so we could, if we wanted to, stop our substitution when we get right to this point. We know we don't have to go any further. Okay, so that's an example of substitution with names. Let's see what happens if we translate this lambda term to use the Bruijn indices and do a substitution. Let's see what happens when we have to implement, when we execute substitution on that representation. So with the Bruijn indices, we're going to replace all variable. We're going to get rid of all the variable names, and we're going to replace them with numbers that tell us how far out we need to go to get to the associated binder. So here's the original name term. We translate it to Bruijn indices like this. I've kept the colors the same. So you can see that even though the number needs to change, they all refer to the same binder because they are, and they're different numbers because they are under different numbers of lambdas, right? So for this purple 4 here, we have to go past 4 lambdas to get to the binder that we need. Okay, how do we do the exact same beta reduction using this form? What does beta normalization for the Bruijn indices look like? Right, so again, we're going to be substituting the 0, 0, 0 term for the blue 0, right? And really also the blue 1 as we go through. So we're going to put in the 0, 0 for the blue 0 and for the blue 1. Now you can see two things that kind of happened when I did this normalization. So one thing is that the second occurrence, I had to increment all the zeros in the term I'm substituting in because I went under a binder, right? So it started out as 0, 0, 0, it turned into 0, 0, 1. So this was one of the things that I had to do while I'm implementing substitution with the Bruijn indices. And the other thing that I had to do is all these purple numbers, I had to decrement them. And the reason I had to decrement them is we did this beta reduction. That meant we got rid of a lambda, we got rid of a binder. And so now these all had to be decremented by 1 because if they refer past the binder that was eliminated, we need to update that. Okay, so now let's do one more example. And this is an example of what happens when we're using a locally nameless representation of lambda terms, right? So a locally nameless representation is kind of mixed. Bound variables are represented just like the Bruijn indices with indices. Free variables are represented by names, right? And so we're going to start with the exact same conversion to the Bruijn indices that we did before, right? Because all of our variables are bound. But as we normalize this term, right, we're actually going to be converting bound variables to free variables until we find that substitution operation. Right, and so we're going to take these two outermost binders and name them. And so we're going to take the term and replace the indices with some new names for them. And I chose W and X for those two names, the same ones that we had before, coincidentally. We don't have to use the same names, but to make the example easier to follow, I'm using the same names. Right, and then we can do our substitution. This time we're substituting XXX for bound variable 0. Notice that XXX has no indices in it. It only has free variables. And we do that substitution. And then after we do that substitution, we're not done. We have to kind of go back out and reconvert the free names W and X back. We have to re-add the binders that we peeled off. And so we finally end up with the same version that we got with the Bruijn indices. We just did things in a different order. And you can see, well, first of all, there's a lot going on. So you can see why it would be easy to make mistakes, but you could also see that there's a lot of bookkeeping that needs to go on. We think of substitution as just this simple, we're doing a recursion over terms, right? But we have to do a lot of bookkeeping, right? We need to know what the free variables are, the term they're passing in. We have to do this renaming the bound variables as we go along. And the variable that we're using for renaming has to be fresh enough. It can't conflict with other names that are already present in it. When we use the Bruijn indices, we saw that we have to do this shifting, right? Both shifting inside the term that we're substituting in based on where it appears in the output, and also shifting in the term that we're substituting into because we needed to lose a binder. And then with locally nameless, we had to do bookkeeping before we even got to the substitution, right? Locally nameless works because it has this invariant, right? Whenever we call substitution, right, we've named the indices that would be free, right? All the indices inside of name refer to binders inside of A directly. They don't refer to binders in any external scope. If it was something from an external scope, we would use a name instead. So to maintain this invariant while we're working with locally nameless terms, we do need to exchange free and bound variables as we're traversing the term. And again, as we are naming these bound variables with free names, we have to make sure that those names are sufficiently fresh. And just to kind of emphasize this difference between the use, so you'll see that names and Bruijn indices, we kind of can use them in a similar way, but locally nameless, when we're using a function that uses substitution, we have to do a little bit of work in the function itself. So to make that clear, I'm going to do a short little interlude and talk about what normalization looks like with these three different implementations. And this also is important to kind of look at this code because it also helps us understand what is the benchmark that we're doing. Because remember, our benchmark is normalization of this big church encoded lambda term. What normalization function are we going to use? Now, one thing I want to caution you is that I'm using this benchmark to evaluate substitution. There are faster ways to implement normalization of lambda terms where you do normalization in different orders. I'm focusing on just a very specific order that's called normal order reduction. It's not necessarily the fastest order for reduction, but it gives us lots of substitutions. And that's the thing that I want to measure. Okay, so let's look at what normal order reduction. In some sense, it doesn't really matter so much, but I want you to pay attention to the interaction with names and binders and substitutions, right? So we have an expression we want to convert, we want to compute its normal form. For some of those expressions, they're already in normal form. Other expressions, we have to do some recursive call. So if we have a lambda that has a binder, and in this version, I'm using a named representation. So my binder, it's going to have a name for the variable at the binder. To calculate the normal form, I just go right underneath. In an application, now here's where the action happens. If we have an application, and we do this auxiliary operation that computes the weak head normal form, it's sort of like a reduced version of substitution. If we do this, we compute the weak head normal form of the function part of the application, and it turns out that it happens to be a lambda expression, then we can do a beta reduction. Here's where we call substitution and substitute into the body of the lambda. If we do this weak head normal form and we don't get a lambda, we don't have the opportunity for a beta reduction. And so we just need to normalize the two components of the application. Now, weak head normal form, I'm going to go through this quickly because it looks very similar. It just does fewer reductions. It stops earlier, doesn't recurse under lambdas, but it does keep looking for binders in the heads of applications. Again, I need some implementation of reduction for this benchmark. This is the one Lennart used, so I'm just inheriting this. The nice thing about this is it does call substitution lots of times. What does it look like? So that was the definition of the function if we had represented bound variables with names. What if we were representing bound variables with Bruijn indices? Looks very, very similar, right? If a variable is still a normal form, whether it's a number or a name, when we're recursive or binder, we don't have a name there, but we still go right underneath. And when we find a beta reduction, the only very small difference is how do we call substitution, right? So when we find a beta reduction, we don't have an X to name, but we do have 0, the index for the variable, for the bound variable there. And internally, whatever definition that we have for substitution, we hope it will do all of that bookkeeping that we need for us. So we'll do the two kinds of shifting that we saw. And as long as it does that, this is going to be our implementation for normalization. And weak head normal form, similar, I'm not going to show it. Okay, now what happens when we do locally nameless, right? So with locally nameless terms, right, it starts off the same, but when we get to a binder, we have this invariant that we're only ever working with terms that don't have any indices to the outer context. And so that would happen when we do a recursive call under a lambda expression. And so that means to maintain that invariant, we have to do a little bit of work here, right? We have to, when we get to a lambda with a binder, we don't have a name. for the binder in locally nameless representation. So we have to come up with some fresh name that doesn't interact with the free variables, the other names that are already in B. And we have to name the variable at this point, at this binder. And we can do that using the substitution. We're going to replace variable 0, the index 0, with this new fresh name that we've created. And this is the term that we do the recursive call for normalization. After we get that result, we're not quite done. We have to turn that, because we get a term that has this x for 0, we want to turn that back into a lambda binder. So we have to go back and replace x with bound variable 0, do the opposite conversion before we put it back together as a binder. So this is kind of the hallmark of working with a locally nameless representation. I'm going to call this operation where we're replacing bound variables and free variables, opening, and its inverse operation, closing. Right. And then in application, the benefit in application is that when we get to our beta reduction, we can still substitute for a bound variable, because that's what here. We don't have to like name it and then substitute. We can go directly substitute for the bound variable, but that substitution operation, it's a lot simpler than the substitution operation that we saw for Bruijn indices. It doesn't have to worry about the shifting that we had before. I've given you sort of a very high level, we didn't look at any code implementations. If you go to the repository, you can see the implementations that I'm drawing from for these 3 different approaches. But I'm sure you're wondering, what's faster, right? There's a lot of work going on in all 3 of those approaches. And so let's benchmark it, right? And so if you're playing along at home, in the repository, there's the lib directory. In the lib directory, you'll see tons of different implementations. We're going to start with 3, which are sort of the basic named representation, the basic Bruijn representation, and a basic locally nameless one. So the first 2 come from Lennart Augustin's lambda-calculus cooked 4 ways. The named representation had a very small bug in picking bound variables, so I'm actually benchmarking the one that fixes that bug. The locally nameless representation, I didn't write this directly. I got it from another tool that can generate locally nameless substitution functions. It generates them in the language of the Cock proof assistant. I manually translated that to Haskell. So I didn't write really any of these codes, but this is going to be our baseline. This is our starting point. 3 kind of simple implementations of lambda-calculus. Right. And so what does it look like if we benchmark them head to head? And you might guess, which one do you think is going to be faster? Right. And here's what I found out. Right. It turned out that they're all fairly close to each other. Like it's not as significant of difference as we saw from the variable from the libraries before, which was orders of magnitude, right? So this is the slowest one, the Bruijn indices, is only twice as slow as the fastest one, locally nameless. And so they're all, I would say they're all kind of in the same ballpark, right? So this is our starting point. And this result, I think it doesn't really tell you enough information to decide, if you're making a binding library, which approach should you do? Right. So of course, though, we know we can do better, right? We should try to optimize. And how are we going to optimize these implementations, right? So how do we create faster versions that still fundamentally look the same, right? So they're still going to look like I'm using names. They're still going to look, or the Bruijn indices or locally nameless. Right? I don't want to have to change any of the code, that the reduction code. All of the difference should kind of be internal, right? And so how am what kind of optimization can I do, right? And I found another tweet that kind of resonated with the kind of optimizations that we do when we are making substitution faster. And if we're Haskell programmers, this should be kind of obvious to us. Let's use laziness. Let's not substitute right away. Let's delay some of these substitutions so that we can, maybe we don't need them all, or maybe we can put them together and optimize them. right? So can we do better? Yes, we can. We saw that there was a lot of bookkeeping going on. That bookkeeping led to many traversals of the term. We don't want to do that many traversals when we're substitution. And so what we want to do is we kind of want to have a sort of multi-substitution, right? So we'll have some idea of a substitution as a type. So this is the type of substitutions, and this is going to be a multi-substitution. It's going to substitute for multiple variables inside of this expression, right? And if we're working with names, our multi-substitution, let's use a finite map, right? Maybe some data.map or data.intmap, a map from variable names to expressions. And then at binders, to make this even more efficient, we're going to store some extra information. We're going to cache, we're going to compute when we create a binder, we're going to compute the set of free variables, and we'll keep that stored. And as long as we use bind as this abstract notion of substitution, this cached information will be opaque to clients. They don't know that this caching is going on, and so they can get the benefit of the optimization without any of the complexity. Right, and so what does this do by just making these two changes, kind of grouping substitutions together so that we can do multiple ones at the same time and caching that free variable implementation, we can speed up our computation of fresh variables because we don't have to keep recomputing it whenever we need it. We can cut off our substitutions because we can look to see whether the thing we're substituting for is actually free in the body. And we can fuse these. We had to do some renaming at the same time as substitution. We can fuse that together. So that's kind of the key idea for some optimizations. I think if you sat down, you might think about some other optimizations. These are the ones that I tried out for the benchmark. What about with the Bruijn indices? How can we use the same idea of optimization to make our implementation that uses the Bruijn indices more faster? Now, one approach is to also generalize the Bruijn index substitution to a multi-substitution. And here, I'm not going to go into the details of how this works, but there's a really nice way to represent the Bruijn index substitution as a substitution for all of the indices inside of a term. And we can defunctionalize it so it's a very small representation. And then that is something that we can delay at a binder, that we can have, whenever we apply a substitution to a lambda term, we don't have to keep pushing it all the way inside the term, right? And what are the benefits of doing that, right? Well, we have this first order of representation of substitutions. You can kind of think of them as an infinite list, but as a very compact version. And when you compose them together, you can often short circuit some of those substitutions and save a lot of work. And that's going to give us that we don't have to do as many traversals, because like if you shift one way and then shift the other way, that's going to cancel out to an identity substitution, which we don't have to apply at all. What about with locally nameless? With locally nameless, again, it's using this mixed indexed free variable version. And so with locally nameless, what are we gonna do? We're gonna delay, and we're gonna observe that when we work with locally nameless terms, we often do a lot of opening and then some substitution and a lot of closing in a row. Let's cache those at binders. We need to remember whether we're doing substitution or whether we're doing close or we haven't done anything yet. Let's cache that. And that's how we can fuse those traversals together. And that's, again, going to give us a lot fewer traversals as we can open up all of the indices in a term at once instead of doing a bunch of intermediate steps. Okay, so let's look at a comparison to see what these optimizations do. And it's rather dramatic, right? So the blue bars are what the original versions are. If we go out and we look at these optimizations, we can see here's where we get our orders of magnitude difference, right? Where we can make these implementations a lot faster. Now, remember, though, that I also cared about having generic interfaces, right? And so in addition to just applying the optimizations to these basic implementations of lambda terms, I also developed took those implementations, separated out the generic part from the client code, and so we can measure the effect of generic programming. Because not only do I want my code to be fast, but I also want it easy to use, right? And so here, this is just so you can see after doing this process, this is for the named version, the code that the name client has to write is a little bit longer from unbound, because not only do we need to know where the variables are, but we also need to know how to calculate free variables. So I have a class for calculating free variables, and I have a class for doing substitution, and I have a class for talking about where variables are. But this is it. This is the end of the code. This gives us our substitution function via generic programming and our free variable function via generic programming, all for free. Now, for full disclosure, when I'm benchmarking it, I'm putting in some GHC pragmas to make sure that we have the full benefit of the optimizer. But the upshot of, even though we have sort of factored all the complexity into a library, when we go and look at the benchmarks where we compare the optimized version against one where we've split things up into two modules, the generic library and the specific just derive my implementations, there's very, very little overhead from the generic programming, right? And so here, I want you to notice that this chart is now in milliseconds. The earlier chart was in seconds, but the overall view, the overall overhead for doing the generic programming is very, very low. And in one case, it even sped it up for reasons I don't quite understand. Okay, so I see that I'm running low on time. I do have a very short coda about strictness, which if you were in the talk that is directly parallel to this one, you would be hearing about strict Haskell and how strictness can sometimes affect the running time of Haskell code significantly. And so I also benchmarked everything that you just saw with a different expression form that made all the components strict. How does that change things? For the simple versions, it has a dramatic effect, but once we get to the optimized versions, the effect is much decreased, and the lazy versus the simple versions don't really change very much, right? And so here's kind of the big picture, right? Just starting with the naive implementations of these operations, it's pretty slow. But if we just sit down and think about ways to delay things, to cache information so that we don't have to redo any of this bookkeeping, and we can use our traversals, we can get some pretty incredible speed ups. And it doesn't even really matter which representation we do. Like, applying the optimizations is much more significant than choosing the right variable representation. Right now, again, it's only one benchmark. Don't read too much into it. To really generalize this work, we should look at many, many more applications of substitution besides computing normal forms, and maybe even computing normal forms for different lambda terms. But even if we just focus on this particular one benchmark, I still feel like there's a lot more to learn, even in this context, right? You know, I showed you how to optimize Bruijn indices and locally nameless representations, but I didn't really get to the same place that these binding libraries were. So maybe there's more we could learn. I mean, we could look at other forms. There's lots of ways to optimize a particular representation. And in this repository is this common framework for testing out these ideas. So if you have some ideas of some optimizations, or if you have other approaches, I welcome contributions to this repository. And I think I'm going to stop here and have time for questions.
Hey, that was awesome. I think the questions should be in the spatial chat, and so everybody wants to join there to ask any questions, and let's see you there.
Okay, I'll see you there.